This is the Electronics Workshop 2, and our project is the 24-hour clock. Our mentor is Dr. Aftab Hussain. My teammate is Abhishek and I am Bolimunta Shreya. The motivation behind our project is building a 24-hour clock without a microcontroller. This helps us understand the basic digital logic design principles. It can be cost effective.
We're having 4 blocks. The first block generates pulse for the entire clock. We have made it using a 4060 decade counter, which also consists an inbuilt oscillator. In the rest 3 blocks, we are using 4026 IC, which is a 14-stage decade counter. In the first stage, we have included two 4060 ICs to add multiple frequency dividers. This stage helps us in generating pulse for the entire clock. We used 32786 Hertz crystal oscillator. The 4060 IC divides this frequency to give us an accurate 1 Hertz, and the output comes out to be 1 second. The 4060 IC is a binary counter with a built-in oscillator. However, we did not use the built-in oscillator as it did not give us an accurate 1 Hertz at the output. We used a crystal oscillator of frequency 32.786 kHz. This binary ripple counter works on the principle of D flip-flops connected in series with each other. This helps us divide the frequency by powers of 2. At the output pins as shown in the diagram, the frequency given as an input is divided based on the mod value at that specific pin. We particularly used mod 1024 and mod 32 pins. When these are cascaded, it gives us a mod value of 32,786, which accurately gives us 1 Hz. To set the minutes and hours, we use different frequencies. For minutes, we use 64 Hz, and for hours, we use 2048 Hz. This essentially helps us fast forward time.
The Mod 60 segment uses the CD4026 IC. This IC is a decade counter. As you can see in the circuit diagram, the frequency from the pulse generator output is given to pin 1. This is displayed on the first 7 segment display. Then the frequency is multiplied by 10 and the output is given from pin 5 of the CD4026 to the cascaded segment's input. After 10 counts in the units digit of the second segment, the 10th digit is updated. Further, a combinational logic was implemented such that the 10th digit of the second segment counts only till 6 and resets to 0. The E, F, G segments, the E, F, and G segments of the 7 segment display are switched on only when the 10th digit of the second segment is 6. Thus, a triple input AND gate is used with inputs E, F, G and the output is connected to the reset pin. The Mod 60 segment for the minutes case is similar to the Mod 60 of the seconds case. The frequency from the output of the 10th digit of the second segment is given as input to the units digit of the minute segment as shown here. The frequency is multiplied by 10 and the output is given from pin 5 of CD4026 to the cascaded segment of CD4026 of the other IC. After every 10 counts in units digit of the minute segment, the 10th digit is updated. A combinational logic is implemented which is absolutely similar to the seconds case. The 10th digit of the minute segments counts only till 6 and then resets to 0. The logic is similar. EFG are connected to a triple input AND gate and the output of it is connected to the reset pin. Similar to the previous two stages, in the Mod 24 stage, which is the hour segment, two CD4026 ICs are cascaded. The hour segment resets after counting to 24. Here, the logic is the 10th segment resets after 2 and the unit segment resets after counting to 10 for 2 times and then counts till 4. So exactly when it reaches 24, we have to reset. This can be understood better with the 7-segment displace diagram. Here, the 10th segment, there is only G that is being used for the number 2. So that is connected to a AND gate, and for the units digit we have 4, and in 4 F and G are used. Thus, first F and G of the units place of the hours segment are given as inputs to the AND gate. This output is taken as an input with G of the 10th digit. The output is used for resetting the entire clock. Here we are using a simple AND gate. The IC is 7408. This is the truth table for mod 60. Here we can see that E, F, G are highlighted. They all become 1 when the value is 6, and that is when the clock is reset. Given below is the K-map of the same. Here is the circuit diagram of our entire clock. The hardware implementations for the second, minutes and hours is clearly represented here. You may play the videos to see each one of them. Here we notice how the seconds is going after 59 to 000. Similarly, in the minutes case, we notice that when it is 59 in the minutes case and 59 again in the seconds case too, the minutes gets reset. In the hours, we notice that when it reaches 23:59:59 in the hours, minutes and seconds case, it resets to 0. Here is the hardware picture of our final circuit. The challenges faced were these. There were too many wires involved while implementing it on a hardware, and a more optimal and organized circuit would have helped overcome this challenge. Further, a single switch could not be used to reset time. We observed abnormal pulses and an X, that is an unknown state, was occurring. Although there was a built-in oscillator in CD4060, it only gives an approximate 1 Hz. This was not accurate to 1 second, hence a crystal oscillator had to be used. Proposed improvements. These proposed improvements have already been implemented, although they were not a part of our project. A stopwatch has been implemented and it has 3 major features. It can reset time, it can pause time, and it can continue time. These have already been implemented in the hardware and have been shown during the Viva. A functional clock was built that accurately displays time using basic electronic components. This project was a great way to learn about circuitry and digital logic and design. Thank you.